Hey everyone, Sanjay Medichurlo here with part two of homework one of my computational methods homework. So in the last part, we coded a higher order function that calculated the Jacobian of our curve, and then in part two, we're going to use Clojure again, explain and code a higher order function that returns functions that calculate the Frenet-Serret tangent and normal vectors for the helical curve. Explain how the radius curvature can be obtained at any point on the helical curve, right? So to do that, let me get OBS out of here. To do that, right, let's actually look at what the Frenet-Serret things are, right? Um, so you have the Frenet-Serret formulas are given as follows, right? Um, um, and so t is the unit vector tangent to the curve, pointing in the direction of motion. So t is the direction of motion of the curve. And so n is the unit normal vector, the derivative of t with respect to the arc length parameter of the curve divided by its length, right? Um, um, and so uh, basically, physically, that's like how the curve is turning, right? And then b is the binormal vector, the cross product of n and t. So that's cross product is perpendicular to both n and t, which you can see in the diagram, and that's how the curve is twisting. So if you go look at our helix, let's graph you real quick. Oh, won't graph. Um, Let me put this at the end. So I'm just gonna say fig at the very end. Okay, yeah. So the tangent would be like if we look at it like this, the tangent would be um, right here, and then the normal would be right here, and then the binormal would be coming out of the page, right? And so to code these, we actually use a definition. Um, so these have to be unit vectors, and then we actually use, where is it? This way to express the tangent vector, right? So it's just the derivative of our regular vector divided by its magnitude, right? And so to do that is actually really easy, right? We're just going to take the derivative of our vector and then divide by its magnitude. It should be pretty easy. So we're going to define a function, Frenet-Serret, which takes in a function, in this case, our curve, right? And then in it, we're going to define two functions, our tangent function and our normal function, right? And so what should the tangent vector function take in? Well, you want to know the tangent vector at any point t, right? So that's pretty easy, right? And then, so the tangent we said was the derivative of our actual function. So df dt. And then how do we get the derivative? Well, it's really easy, right? We can use the Jacobian that we used in the last time. So we can say df dt equals Jacobian of f, right? Because it's the derivative of f, right? And then what we have to do is find the magnitude of this vector, and to find the unit vector, divide by the magnitude. So we're going to say magnitude. And then we're going to use a function JNP linear algebra dot norm, which actually finds the magnitude of our vector. And it's going to be df dt at our point t, right? And then so our tangent vector equals df dt at point t divided by the magnitude, right? And then we're going to return tangent. And then we're going to do the same thing here, except if you look at the Frenet-Serret definition, the normal is basically the derivative of the tangent, right? So instead of using the function, right, um, we're going to use the tangent. So it's going to be dn dt, equals Jax.Jacobian of t, because we're taking the derivative of the tangent. And so this magnitude equals J&P dot linear algebra dot norm df, no, not df, d, what did I, yeah, no, what, how do we want to do this? dn dt, right, at point t, and then the normal vector just simply equals dn dt at t divided by the magnitude. And then, oh, yeah, mag 1. And then we return normal. And then for the outer function, the Frenet-Serret, we want to return tangent and normal. So how do I use this, right? Let's just say tangent normal, or tang and norm, equal Frenet-Serret of f, right? And then I want to find the tangent vector at 0. Sorry, I didn't mean to do that. And the normal vector at 0. Actually, let's do it like this. All right, please work. Uh-oh. The numpy was, should it be f? Oh, it's because I called f, but I should be calling f Jax because we want to use the JNP version. That'll do it. Look, and now we get the normal array. We get the tangent vector, 0.99.13, and then the normal vector, -1, 0, 0. So if we go, please, come on, bear with me here. So when t equals 0, cosine of 0 is 1, so x equals 3, y equals 0. And physically, it's a little hard to see on the graph, but these represent the physical relationship of the tangent and normal vectors that we talked about, right? So we've done that part. It's pretty easy. And then let's see. We need to explain how the radius curvature can be obtained at any point um, along the helical curve, right? And if we look at our Frenet-Serret, um, so for example, the tangent, right? Or even the normal, dt ds equals k, or kappa, which is the curvature, times normal, right? And so basically, our normal vector and our curvature have a inverse relationship. So if we wanted to find the curvature at any point along this curve, we find the normal vector, right? Um, we find the magnitude of the normal vector, um, and then we would take 1 over that to find the curvature. And so that concludes my video for part 2 of computational methods homework. I'll see you guys in part 3.